Hello, in this video we will see the second example to partial fraction expansion, which is a different case than we saw in the first example. So here we'll make use of the previous video where we talked about factoring out and finding the factors of a polynomial with degree 3. We have this special case here where you just have x cubed minus a number. So now first, we need to find the factors of the denominator. So we know that x cubed minus 1 is equal to 0 when x is equal to 1. You can solve for it and that's what you will get. So you know that x minus 1 must be a factor of x cubed minus 1. We should now do the long division. So x cubed plus 0x squared plus 0x minus 1. So what do you need to multiply x by to get x cubed, and that's x squared. So you get x cubed minus x squared and you subtract that from here. So you end up with positive x squared. You bring down the 0x. What do you need to multiply x by to get x squared, and that's just x. X times x is x squared. Negative 1 times x is negative x, and we subtract that from here, so we get positive x. We bring down the negative 1. X minus 1, what do you need to multiply it by to get x minus 1? So that's just 1. And x minus 1, so that's 0, so we get a remainder of 0, which makes sense. Remember that when you're multiplying something by a factor, you should always get a remainder of 0. So now we know that the two factors of x cubed is x minus 1 and x squared plus x plus 1. And we have a and b. And we want to find a and b just like we did in the previous example. So we have a times x squared plus x plus 1. So remember that you need to multiply this first term by x squared plus x plus 1 in order to get x cubed minus 1. And so if you need to multiply the denominator by that, you must also multiply the numerator. So that's why you get a times x squared plus x plus 1. And you do the same thing with b. If you didn't quite get my explanation as to why you need to multiply a times this and b times this, you can always go back to the video where I explained the concept of partial fraction expansion. So, okay, and we want this to be equal to 3x squared plus 7x minus 1. And so now, first let's just substitute x by 1 to make this equal to 0. And that way we know we can get rid of this term and only have a as a variable. So x minus 1 is equal to 0 when x is equal to 1. And so this just becomes 0. We don't care about this term anymore. And so a times 1 plus 1 plus 1 is equal to 3 plus 7 minus 1. And so we have 3a is equal to 9. We divide both sides by 3 and we get that a is equal to 3. So we can replace the a with a 3. And so now we want to find what b is. So when your denominator is a polynomial with degree of 2, your numerator must be of degree 1. And let's see how we can find what b is. At least degree 1. It could be just degree 0 if occurs. So knowing that b is at least degree of 1, we know that b can be written as lowercase bx plus c. So let's just replace b with that. So here we have b x plus c. And now we'll find what this is. So here, if we make x equal to 0, we actually successfully get rid of b. Right here, we know what a is, so there's no issue with trying to get rid of it and finding it 0. I mean, we could have done it in the previous example. Here, we don't really know what the zeros of this polynomial are, so it's just easier to try to substitute for a as 3. So if we let x equal to 0, just so we can get rid of this b, we get 3 times, well, 0 plus 0 plus 1 plus, and this is just 0 plus c times negative 1, which is, well, 0 minus 1 is equal to 0 plus 0 minus 1. So here we have 3 minus c is equal to negative 1. And so we subtract 3 from both sides. And we get negative c is equal to negative 4. And we divide by negative 1 on both sides. We get that c is equal to 4. So here we replace b with some bx plus 4. We know that c is 4 already. So now we want to find lowercase b. So to find the lowercase b, which is the coefficient of x right here, we just find another x which is not 0, so that way this doesn't become 0. So let's choose, for example, 2. And we know what to substitute a and c by. So we are left with only one variable, which is lowercase b. We don't want to substitute, for example, with a 1, because we would actually get rid of this term. Maybe instead of 2, let's substitute with negative 1, because it would be easier. So we have a is equal to 3. Negative 1 squared is just 1. And minus 1 plus 1 plus, and we have negative b, and then we found c to be 4, so plus 4, and then negative 1 minus 1, that's negative 2, that's equal to 3 minus 7 minus 1. Okay, very well. So now we have 3 times 1 plus 2b minus 8 is equal to negative 5. So actually, here, if we solve for b, we get that 3 minus 8 plus 2b is equal to negative 5. This is equal to negative 5. So we add 5 to both sides. And we get 2b is equal to 0, which means that b is equal to 0. So as I said before, you know that the numerator of this degree of 2 must be at least a linear component, a degree of 1 polynomial, but I'm sorry, at most a degree of 1 polynomial. However, here we find that b is actually 0, so we're left with only 4. That doesn't always happen. This is just something nice about this equation, that we're left with only numbers in the numerator. But you could be potentially left with a a linear term at above this as a numerator for our degree 2 polynomial, and that would be fine. It's just that in this case b was equal to 0.